Alright, welcome. It is Unit 1, Lesson 1, What is Calculus, and also Intro to Limits. So this is 2 sections in our Larson textbook. So this is just kind of like some screen grabs from the book, and we're going to talk a little bit about it. So what is calculus? It's thinking about how things change. Velocities are how position is changing, acceleration is how velocity is changing, but also how we have tangent lines, slopes, areas, volumes, arc lengths, centroids, curvatures, all kinds of fun and exciting things that you can, if any of those words are unfamiliar to you, feel free to journal about them. But these are things that can model real life situations, and that is the beautiful thing about calculus, is that it covers how things change in a way that we can still quantify. Some students try to learn calculus as if it was just memorizing a bunch of new algorithms. And while that is possible, and you will have a functional ability to do things, that computational mindset leaves you in the space of being a computer. So you are not a computer, you have a brain, and you can do more than that. So figuring out how patterns happen, how things look, and gaining a deeper understanding of how we can analyze things around us that is one of the beautiful things about calculus. So let's look at some comparisons. Without having the calculus, we can only find the value of a point, a function at a point. With calculus, we can think about the limit, how the motion of a function behaves as it approaches somewhere, even if, see how there's a hole there, even if there is a discontinuity. And we're going to talk a lot about continuity. That is a big thing in this first unit. Without calculus, you can think about the slope of a line, because it's just rise over run, right? Delta y over delta x. But with differential calculus, you can think about slopes of curves. How a curve, a not straight line, can have a slope, and what that is going to be, what that means about the function. For no calculus, you can deal with a secant line, meaning that it goes through at two locations. And with differential calculus, we can find a tangent line and its related slope. You can think about, without calculus, you can think about the average rate of change, because you just look at how far it's gone based on how much, and divide that by how much time has passed, and you get an average rate of change or an average velocity. But with differential calculus, you can think about what the instantaneous rate of change is. At a particular time, what is that speedometer saying? So that is very, very exciting. And we will talk about in this class how it doesn't really make sense how some of our traffic laws are enforced, and if they trusted the math, then there could be a lot more traffic law enforcement, which is interesting, I think. We can also think about how long things are, right? Lengths of things, it's something we've talked about for a really long time in math, but without calculus, we can think about how long a segment is, a line segment that's straight. With calculus, we can think about how long something is, even if it's curved, because we can handle having curved lines, which is very, very exciting. Without calculus, we can find a surface area of a cylinder, right? So this is just a circle that's kind of projected along this axis. With calculus, we can think about the surface area of a solid revolution, where we have this curve, similar to the one we have up here, and we can rotate it around this axis in order to get this very nice looking surface. And this surface, we can figure out what that surface area is. It has applications. Without calculus, we can figure out what the mass of something is, as long as the density of that object is constant, like a bucket of water. With calculus, we can think about the mass of a solid, even if it has a variable density, even if the density of the object is different at different parts, which is pretty cool. And we can also find volumes of things that are not just, prisms and stuff like that, where I think, memorized a lot of different formulas for volumes of things without calculus. But with calculus, we can find volumes of those shapes, but we can also find volumes under a surface, which doesn't have to be necessarily a rectangle. It's pretty amazing. So just drawing a little bit of connection. So we have the slope of a secant line through this point C and comma f of C. So this is, it's like this point. This is point C comma f of C. And another point, which is this backslash delta, which is me secretly trying to get you all to learn LaTeX. But it's actually, this should be a capital D for delta to get you this symbol for x away. So you're looking at this point and then some delta x away plus a delta x to get you there, or over here where this point is, or over here where this point is, something like that. So the slope of that line, well, slope is just the change in y divided by the change in x, is it not? So if we plug in our point C and f of C, and also our point C plus delta x, and our and evaluated and our function at C plus delta x, then we have 2 points that we can plug into our slope formula of, well, this is also like y2 minus y1 over x2 minus x1. And so what do we end up with our slope? We get f of C plus delta x minus f of C divided by C plus delta x minus C. But then there's something lovely happening here. These C's go away. And we have f evaluated at this location and f evaluated at this location, which, you know, we're just going to leave those alone. And we have our denominator is just delta x, which is what we wanted in the beginning anyway. So you see how there's connections. If we do a little bit of algebra, we can take familiar things with unfamiliar things, put them together, and we will be very happy. This has a name. This is called the difference quotient. Difference quotient. I think I spelled that right. Difference quotient. And evaluating these is very exciting and takes more algebra than a lot of you might feel like doing right now, but it's good for your brain, so do it anyway. Difference quotients. And that is an optional practice. I think it's on Canvas somewhere or something like that. I didn't realize this was cut off, so I think I put it in now. So you should be able to see the y1 and the x1 now, so that we can have the whole expression that we were looking for. Okay, how can we figure out what this area under this curve is? Because we just said that we can, using calculus, we can figure this out. But we can't actually do this right now, which is very sad, but we will get there. However, we can approximate this. And we can approximate just by drawing some rectangles. So some lovely rectangles. Look at that rectangle. It's a really bad rectangle. We can pull this rectangle there, maybe one here. And that's like an okay approximation. Maybe there's a better picture down here. There totally is. So finding the areas of rectangles can get us pretty good approximations, and especially if we have more rectangles. More rectangles are very, very helpful for finding areas of things, and that is something that we are going to be looking at with integrals. Very exciting. So, the question for these is this pre-calculus or calculus? So, do you think that finding the distance traveled in 15 seconds by an object traveling at a constant velocity of 20 feet per second is pre-calculus or calculus? It's pre-calculus! Do you think find the distance traveled in 15 seconds by an object moving with a velocity of 20 plus 7 cosine t feet per second is pre-calculus or calculus? It's calculus! Cool. And that is the end of section 2.1. So let's look at section 2.2. Introduction to limits. Suppose that you are asked to sketch a graph of this function. And looking at this function, you're like, difference of cubes, so I can factor that with some crummy sops. Crummy sops. Cube root, so x minus 1 for the cube root of these two, cube root. And then ops, so this is square, so x squared, opposite sign, product, so 1 times x is just x, and square, so that's a plus 1. and make sure we did that right by distributing this out. So x times x squared is x cubed. That's good. X times x is x squared. X times 1 is x. Negative x squared, so that cancels. X minus x, that's good. And negative 1, cool. So we factored that correctly, remembered things, which is good. And then we have x minus 1 in our denominator here. And look, this is lovely. Look at that. These cancel out, so we can have a removable discontinuity. Removable discontinuity. I think I wrote that correctly. Which means that this graph is going to look like this parabola. That's a x squared plus x plus 1. That's a parabola. That's a quadratic. And the only thing that's different between a parabola and this function that we have is that there is a discontinuity at x equals 1. So this is taking care of that discontinuity. So looking at this is going to just be an upward-facing parabola, just a quick sketch like this. But then at 1, it's going to have a hole. Okay, so notation-wise, we have the limit of f of x as x approaches 1 is going to be equal to 3, because if we just plug in 1 into here, we get 1 squared plus 1 plus 1, that's 3. Okay, very good. And we end up with this graph. And this hole still has a limit, and we'll talk more about limits in a little bit. We're encouraged to tackle limits is just by plugging in stuff that's nearby what you're looking for. So remember, we were looking at the limit as x approaches 1 of f of x. So we're going to plug in numbers that are less than 1 over here. We're going to plug in numbers that are greater than 1 over here, and we're just getting closer and closer to 1, but not actually evaluating at 1 because it breaks that function. So if you just plug those into whatever calculator thing you like the best, I do recommend Desmos, though you should probably get used to using your TI-80 whatever something, or your Casio whatever something, that as long as it's allowed on the exam thing. Then you can see that these numbers approach 3. Approaching 3 from above, approaching 3 from below, right? Because 2-point stuff is smaller than 3, and 3-point stuff is greater than 3. So we're kind of squishing in to get to roughly 3, but it's not going to actually be 3, because when you plug in 1 into your function, you're going to get out undefined because of the algebra that we did up here, right? You get undefined. So the limit is going to be the number 3, but our function evaluated, like if you tried to do f of 1, then you're not going to get anything that's helpful. The way that we read this is the limit as x approaches 1 of f of x is 3, or you can switch these, the limit of f of x as x approaches 1 is 3. Reading this in order, it doesn't really matter to me which one you choose to do first. But the most important thing is to keep in mind that a limit is a number. A limit is a number. So when we have this notation, what we have this equal to is a number. The only thing that we can have for a limit value is a number. If you get infinity, that means that it's not a number, so that limit does not exist. So in this example, we're going to talk about how to estimate something numerically, and estimating means that you're plugging things in and just seeing if it works. Numerically means that you're plugging in numbers. So this is effectively, you're just making a table the way that we did in like the other one where we were getting closer and closer to 3. This, we are just plugging in values, and we're going to do that, I think, using Desmos. So what we have here is Desmos, and I typed in f of x equals in order to get this part to show up. And I added, with the plus button, I added a table. Then I renamed the top of the second column as f of x sub 1, because the x sub 1 is going to be what the values are in this column that we're substituting in. So we were looking for evaluating our limit as x approaches 0. And so that means that at 0, You better believe it, it is undefined. See that? It's undefined. So when we plug in 0, we get undefined. But as we are approaching 0 from the right, so this number is greater than 0, so like 0.1, okay, we're getting like something like 2. If we're approaching 0, let's get a little bit closer, 0.01, we're getting even closer to 2. And if we approach 0 from below, so we get negative 0.1, and we get something over there, negative 0.01, and we are getting even closer. With all of that, what we have is that this limit is going to be a number, and that number is 2. Link if you are interested. So for this one, we got to find the limit of f of x as x approaches 2, where we have this piecewise function. And what we get with this piecewise function is this part of our domain, we have our function evaluated at 1, and this part of our domain, which is a very small part of our domain, we get our function is evaluated at 0. So quick sketch, just to see what we're looking at, is let me change this color, so for the x is not equal to 2, so this is 2 right here, then our function is 1, except at 2. And at 2, our function is going to be evaluated at 0. So that is going to be what our function looks like. And so what is the limit, or what is the number that we are getting closer and closer to as x gets closer to 2? So as we're getting closer here and closer here, what do we have? 1. So our limit as x approaches 2 of f of x equals 1. What about if we have this? Oh, I kind of ruined it. So if we have this behavior that differs from the right and the left, we need to show that this limit does not exist, that we don't get a number. Not a number. Or N-A-N, that's like a thing in computer science stuff, I think. Not a number. But what is actually happening in this function? We have the absolute value, so that's always positive, divided by the not absolute value, which could be positive or negative. And what's happening when we get closer and closer to 0, which is between the positive and the negative numbers. So what happens? Well, actually it's in this graph, which is quite lovely. And what we have is a jump discontinuity. This is a lowercase delta. And that is going to show up in our formal definition of limits. That is something that you will explore in your college math endeavors. Deltas are the small changes in your x values. Epsilons are the small changes in your y values. It's a very important thing, but we are not going to do it too much in this class. But what we do have is that as you're approaching 0, as x approaches 0 of this function, this absolute value of x over x. When we're coming from the left, we're getting negative 1. When we're coming from the right, we're getting positive 1. And since negative 1 is not equal to positive 1, those are not the same number, so our limit does not exist. Limit does not exist. Limit does not exist. What about this? What happens to this function? It is unbounded. Unbounded meaning maybe infinite. So what happens to this function 1 over x squared as x approaches 0? That means that our denominator is getting closer to 0, which means that this function is blowing up into infinity. And since we have x squared happening, then the sign of this is always positive. This is always going to be a positive thing. So we're always getting positive infinity, because if it was like 1 over x, then it could go up to positive infinity or down to negative infinity depending on the sign of x. So here, the limit that we have is still not a number, because infinity is not a number, right? Infinity is a concept. It's an idea of the biggest number possible. And so that's not actually a number. So this limit, the limit as x approaches 0 of 1 over x squared, does not exist. Does not exist. One more kind of not existing limit is the limit as x approaches 0 of sine of 1 over x. So sine is an oscillating function, right? And if we take what's going into sine and we're making it 1 over x, that means that the input is either positive infinity or negative infinity that's going into our sine. And what happens to sine as it's going to positive or negative infinity? It keeps on oscillating. Therefore, we get this crazy thing happening. You can have a fun name for it. It's called a growl. That's not a real thing, but that's the thing for remembering what's happening. We have a growl happening. Therefore, we don't have a limit because we keep on oscillating. It just keeps on going up and down and up and down and up and down. And if you don't believe me, put this into Desmos. And then zoom in as much as you can. It's crazy. So finally, the formal definition of a limit, I just feel like I should say this, is let f be a function defined on an open interval containing c, except possibly at c. So that means that at that particular location, it doesn't have to particularly exist. And let L be a real number. So a limit is a number. The statement, limit as x approaches c of f of x equals L, means that for each epsilon greater than 0, so this is epsilon, there exists a delta greater than 0, this is delta, such that if 0 is less than the distance between x and c, and that's still bounded above by delta, so that means we have a very small x distance. The x distance, the horizontal distance, is very small. Then the absolute value of f of x minus L, which is the distance in the vertical direction of f between f and L, f of x and L, is bounded above by epsilon. And so this boundedness is really key to describing, using math, what a limit is. We have this lovely picture. So the closeness in the horizontal direction determines the closeness in the vertical direction. And if we get the epsilon band to be small enough, then with a close enough delta, then we do have a limit that exists, which is pretty dang cool. All right, I think that's it for this video. Have a wonderful day.